Good morning to everyone. So our today's lead code question is 1382. That is balance a binary search tree. So in this question we are given a binary search tree and we have to make a balanced binary search tree from the given binary tree, right? And if it is given, if there are multiple possible answers, then we can return any of those answers, right? So what is a binary search tree? We will see two question: what is a binary search tree and what is a balanced tree, right? So first of all, what is a binary search tree? A binary search tree is basically a tree who has uh, like all the elements are at every node. All the elements that are smaller are will be present on the left side of the node, and all the elements that are larger will be present on the right side of the node. So suppose here, if you'll see, wait here. So suppose if you'll see this example, so see, one in one is our root, right? So two is larger than one, so it is present on the right node. Three is larger than two, present on the right node. Four is larger than three, present on the right node. So basically, it is a binary search tree. So in binary search tree, if and suppose if we have what we called minus one, no, not minus one, suppose if we have some smaller element than 2, then it would have been present here, right? So this is a binary search tree, right? And what is a balanced tree? What is a balanced tree? So a balanced tree is a tree that, suppose this is a node and it has some uh, subtree on its left and a subtree on its right. So the difference of the height of left subtree and the difference of the height of the right subtree should be less than equal to 1, right? So that's a balanced tree. So we are given initially a binary search tree, and from that binary search tree we have to return a balanced binary search tree. So for this example, 1 2 3 4, if you'll see this, so here we are given 2. This is one of the answer, possible answer: 2 1 3 4. So if you'll see at this node, there are no left and no right. So height from left and right ka difference is 0. At 3, no left, means from this side height is 0, from this side height is 1, so difference is 1, right? Similarly at 1, height of left and right is, difference of height of left and right is 0. At 2, if you'll see, this side will give us height 1 and this side will give us height 2, so difference is 2 minus 1, that is 1, right? Similarly, if you'll see in this answer, the at 1, height of left is 0, height of right is 1, so 0 minus 1, it is minus 1. So yeah, allowed, means the difference can be either minus 1 0 or 1, right? At 4, there are no left and right, so height, difference of height is 0. If you'll see at 3, here the height is 2, height from left is 2, height from right is 1, so difference is 1. So what we have to do is we have to return a balanced binary search tree from the given binary search tree. So in next example we are given 2 1 and 3, so it's already balanced, so no need to rebalance it. If you'll see the constraints, the number of nodes that can be present in the tree is up to 10 ki power 4, right? Number of nodes can be up to 10 ki power 4. So maybe initially you are thinking of what, like, taking each node and then trying making a binary search tree and then checking if it is balanced or not. But this can be very, like, the time complexity will be very large in this question, because checking for all the 10 ki power 4 nodes and then after that making tree from those nodes again takes 10 ki power 4, and then checking if it is balanced or not again 10 ki power 4. So basically 10 ki power 4 into 10 ki power 4 into 10 ki power 4 time complexity. So this approach won't be a good approach, it will be giving us TLE, right? So we have to think of some better approach, right? And the node values can be up to 10 ki power 5. So let's see the approach. So if you'll see and if you'll think what we want at every node, so if it is a node, what should be there at this node such that the height of the left part and the height of the right part should difference should be less than equal to 1. So this is what we want: height at left subtree and height of right subtree should be less than equal to 1. That is, it can be minus 1 0 1. This is our goal. So using this formula, like this only, this formula will be making our approach, right? This is the basic part which will be formulating our approach, right? And also, as we know, our tree is binary search tree, right? That means at any node all the smaller nodes are present on the left side of the tree. Yeah, we can say left subtree, and all the larger nodes are on the right side. Yeah, that's the basic condition of binary search tree. So this will also helps us in making an approach, right? So what we do is we can what so as you from all the above two things, what we do is at every node, at every node what we want to try is to make the number of nodes on both the sides almost same. Suppose if this is a node and number of nodes on this side and number of nodes on right side, we'll try to make those nodes as the count as similar only, so that the height of the trees should be balanced. So if we get all the nodes, if we get all the nodes from our given tree in sorted order, right? That's so that what we called as in order, and store them, right? So if we get all the nodes in sorted order and store them, then suppose we get our nodes from this way, we get our all the nodes in the sorted order. Then what we can do is we can take the middle element, we can take the middle element as the main node, or we can say like we take this as the main node. Then as our tree is binary search tree, so all these nodes will be present on the left part of this, and all the nodes after the mid to the last part will be present on the right part, right? Again, in this part, if we'll take the mid element as this node, then this part will be present on the left side of this, and this part will be on the right side of this. Similarly, in the right part, if we'll take the mid element as this node, then this part will be present on the left part of this node, and this part will be present on the right part of this node. So what is our approach? We are equally distributing the elements on the left side and right side, right? So that will make our tree balanced, because the number of nodes at each node on the left side and on the right side is almost equal. Means there can be a difference of either one node, right? But the number of nodes on the left part right part is almost equal, because we are distributing it in such a way, right? So if you'll see, all the nodes from 0 to mid will be in the left part because of the subtree, because it is a binary subtree, and all the nodes that are smaller than this will be in the left subtree. Greater than this are in the right subtree, that is mid to last. So this is the core concept of our approach, right? So if you'll see an example, so we are given 1 2 3 5 6 7 8 9, right? So number of elements is 3 4 5 6 7 8. So which one is the middle element? Let's take 5. So we make a node as 5. Then 1 2 3 will be on the left of it. So which is the middle element from 1 to 3? So 2 is the middle element. So we make 2. Then 1 is only present. So 1, right? Then in the right we get 3. Now this side we have 6 7 8 9. So which one is the middle element? So 7 is the middle element. On the left of 7 we have only 6, right? So 6. On the right of 7 we have 8 and 9. So which one is the middle element? If we'll see, 8 is the middle element of that, so 8. On the left of 8 we have nothing, but on the right of 8 we have 9. So if we'll check, is it a balanced binary search tree? At 9, both sides will give us high difference 0, so 0. Here 8, 0 minus 1, it will give minus 1. At 7, 1 and 2, 1 minus 2, that is minus 1. At 3, 0 minus 0, 0. 1, 0 minus 0, 0. 2, 1 minus 1 equal to 0. At 5, this will give us height 2, this will give us height 3. 2 minus 3 equal to minus 1. So at each node the height difference is either minus 1, 0 and 1, means that is considered, right? So I hope you are getting the uh, approach. So basically what we are doing is equally dividing the elements, to the left part and right part, and again out of these elements again we are equally dividing to the left part and to the right part. Here also all the elements on the right side we are equally dividing to the left of it, to the right of it, so that the height from the both side is almost equal, almost, right? So let's see the overall steps. So first of all, what we need is we have to find the in order of the given tree, because in order will give us the nodes in the sorted order, right? And then at every node we have the elements from low index, that is initially 0, to the high index, that is the total number of elements. Then what we do is take the middle element as the node, right? Middle element as a node. Then all the element from low to mid minus 1, low to mid minus 1, this is the mid one, right? Low to mid minus 1 will be in the left part, and then mid plus 1 to high will be in the mid plus 1 to the high in the right subtree, right? And then again we will be taking mid from this part, low to mid minus 1. If we'll take mid, then this will be a node, then this part will go in the left part of this subtree, this part will go in the right part of this subtree. And similarly we keep doing until our low is less than equal to high, right? Our low pointer is less than equal to high. Else what we'll do is, else we make the node as the null pointer. And what null pointer show? That this is the, there is no further nodes, like this is the last node. We can either write is null, or we can write it as null null pointer also, right? Let's see the code part. So we are given a balanced binary tree root, right? So we have make a vector of type tree node star and named as value. So we have called a function, in order function on the tree root, and passing the what we call a vector value. So this is the in order function. So in order function what we are doing is, suppose this is our tree somewhat like this. So at every node we go and check whether the node is not equal to null. If it is not equal to null, we will go to its left. So initially we go from here to here, again check not null, go to its left, not null, go to its left. Its left is null. So what we do is we will push this value in the vector, because this will be the smallest value in this. We pushed it, and then we go to its right. Its right means it is null. No. Now for this node we have checked its left, then we push this node in the vector, go to its right, and uh, check. Now go to its left, nothing is there, push this, go to its right, nothing is there. Now we are done with this node. We go to, uh, we will backtrack to this node. As left is done, means second step is push, then we push this in the this, then call its right. So by this function, by this in order function, we will get all the nodes in the sorted order, right? First, second, third, fourth, fifth, and sixth, like this. And then what we are doing is we are making a tree node star tr initially as null pointer, and then calling another function make tree, passing this tree node star initial index 0, high index, the size of this, that is the value are, that is the total number of nodes, and there are that vector. We are passing these three things, right? So let's see the make tree function. So what we are doing in the make tree function is, so we have tree node star root, low pointer, high pointer, and our uh, vector that has all the nodes that we have taken from the initial binary search tree. So there are two cases: if low is less than equal to high, or low has become greater than high, then we are making it null pointer. Else what we are doing is, we are finding the middle of the low and high. So suppose this is our array initially, this is low, this is high, so we find the middle element and then make that element as the root. Root is equal to va of mid, right? This is the root. We make that is as va of mid, and then we call with root arrow left, root ka left pointer, and then values is from low to mid minus 1, means low to mid minus 1, all these values will be gone to the left part, right? And call root arrow right, right, this right, and the values will be from mid plus 1 to high, means these values. Now again our recursion will do the same thing here, find the mid, and then again call the left part, again call the right part, same thing here. So this way will be getting a balanced binary search tree. I hope I am able to explain you guys properly. So if you liked it, please make sure to like, share and subscribe the channel. Thank you.